In the previous video, we looked at how you can use things like the lookup tables and software and other stuff like that in order to find some of the properties of our system if I happen to know two independent intensive properties. But I mean, that's kind of annoying, right? I have to look at these tables, or I have to use this software, and I have to find it for each individual point. It'd be a lot easier if I just had an equation that I could use, and I could just throw at it. I could put my properties in there, and I can get the other properties. And that's kind of what we're going to do with the ideal gas law. So this is an idealization of our gas. It's based on the kinetic theory. So basically it makes some assumptions like the particles are in constant motion, there's no forces between them, they don't really take up any volume, they're kind of randomly distributed, moving around, low pressure and high temperature. If you compress it too much or you bring down the temperature, this kind of breaks down, and the internal energy is proportional to the temperature. And then from this theory, we can show both experimentally and theoretically that you get kind of these three equations that come out of it. The first is that the volume is inversely proportional to the pressure. So basically, as you compress it more and more and more, it takes up less volume. The second is that the volume is proportional to the temperature. So if I heat it up, it takes up more space. And then third, the volume is proportional to the number of atoms I have. This N is actually the number of moles. Little chemistry side tangent here. A mole is basically just like a group of atoms. It's 6.022 times 10 to the 23rd. So basically just like a massive collection of atoms is one mole. It's kind of like a dozen. If you think about like eggs or something, it can have half a dozen eggs or something like that. But it doesn't change the fact that this means that the volume is proportional to the number of atoms that we have. So now if I combine all of these, what I'm going to get is that my volume is proportional to temperature, number of moles, and inversely proportional to pressure. This also means that my volume has to be equal to some constant we call R times Tn over P. And then usually you'll see this rearranged. We'll multiply over the P, and we'll write it as PV equals nRT. This right here is our ideal gas law. And this is usually how you'll see it written as something like in a chemistry context. But we're not doing chemistry. And number of moles isn't really something we have access to. You know, if you're looking at a power plant, you really know how many moles are flowing through there? Probably not, but you do know how much mass there is. And so what we want to do is we want to rewrite this in terms of mass. And the way we'll do that is we'll call this actually RU. It's the universal gas constant. The gas constant we're looking at is species dependent. So it's going to be different for air, nitrogen, oxygen, things like that. And it's equal to the universal gas constant divided by the molar mass, where my molar mass is basically how much mass I get, so like kilograms per mole. Now I can also go ahead and I can rewrite this real quick. I can say RU has to equal RR times M. Now if I plug this in up here, what I'm going to get is that, let me bring this down like this, PV equals N times R times M times T. But remember that M is just how many kilograms of mass I get per mole. And this N is my number of moles. So these are going to cancel out. And my final equation is PV equals mRT. This right here is the ideal gas law as we're going to see it in thermodynamics. We can also go ahead and rewrite this so we divide over our mass as like P times specific volume equals RT. There's another way you can rewrite this. Sometimes it's easier because all of these are independent intensive properties, and so it makes sense that we have three of these and then a constant. So if I can find any two of these, I can rearrange the equation, do a little bit of algebra, and find the other one. Now if we have the same material, like the same gas, as we go through a process, then this R is going to be constant the whole time, right? So if I go ahead and I solve for R, PV over MT equals R, I know that this has to be constant as long as I'm using the same gas. So if I go ahead and I basically look at this over some process, I can say that initially my P1 V1 over M1 T1 has to equal whatever it is finally. So P2 V2 over M2 T2. And these right here are going to be the two big equations that we're going to be using in ideal gases. So this the second one right here is basically for some process. If we have to know how it's changing, usually you can simplify this because some of these are going to be constant. So for example, let's say I have a closed, like rigid tank. Well, if it's a closed rigid tank, that means I'm not adding mass, right? It's a closed system, so I already know M1 equals M2, and I can cancel those. And then usually it's also going to take up the same space, so I can go ahead and I cancel out my volume, and now I only need to know 3 of these, and then I can find the 4th one. So these are some simplifications you can make. And then the other equation that you're going to be using is this one right here. These are kind of the same equation. PV equals MRT, or P times V specific equals RT. Now technically, there are some other approximations of the gas that you'll see. So you can look at things like the van der Waals equation, and there's also like the compressibility factor. So basically the way that this works is PV. Normally we have PV equals RT. But basically we're going to add in a factor for how it varies from the ideal behavior. So we write PV equals Z RT, where Z right here is just how it varies from our ideal behavior. So if they tell you like Z is 2 or something, you just plug this in and use the same equations as you were using before. So that's one thing you might see. This is kind of like an other. It's not usually too like reasonably seen, I would say, most of the time, that you're just going to see the normal ideal gas. And then another kind of on the side thing is some vocabulary. There's something called a polytropic process, which basically means that there isn't like a great intuitive way to do this. It's mostly just like a notational thing. But basically polytropic, it means that P times V to the nth power is constant. So for example, if my N is 0, then this term goes away and I just have constant pressure. If my N is 1, wow, this program sometimes. PV equals constant, which if I'm looking up here with PV equals RT, technically it's be PV equals MRT, but as long as we're looking at constant mass, this R is constant. In some idealized cases, for ideal gases, a lot of the time, this means that temperature is constant. And then lastly, as our N approaches infinity, this V gains more and more and more influence compared to this P, so we basically approach a state where our volume is constant. So if they tell you it's a polytropic process, this is kind of what's going on. And now the second thing we need to look at is something called specific heats. So basically the specific heat is asking how much energy I need to add in order to change my temperature by 1 degree C. Man, this program is just not having a good time today. What is going on? Okay, so the first one we're going to look at is the specific heat at constant volume, which is CV. This is equal to the change in internal energy per unit change in temperature. You'll notice I'm using lowercase deltas. That's just kind of a notational thing with this textbook. Basically the way that they write this, if I add up, man, it's saving so much. Okay, so if I add up my delta U like this, it's not necessarily equal to U2 minus U1, whereas I'm looking at du, they say that this is an exact differential, while this is inexact, has to equal U2 minus U1. So basically U can just be some weird function that doesn't behave nicely as a differential, and same thing for T. But basically all we're saying is the change in specific internal energy divided by the change in temperature. So if I change it by 1 degree Celsius, how much energy do I need to add to do that? If you think about our constant volume system right here, basically I can add energy by heat, and I can add energy by doing work on my system. And there's not going to be any mass transfer really, because we are looking at constant volume. Theoretically, you could be doing mass transfer. But yeah, that would just be, you would add your sum of M in and M out and all of that. Basically, all of the energy that we're adding has to equal our delta U. And technically, there will be a delta KE and a delta PE here. But remember that we're talking about our idealized gas. So they're basically going to be randomly bouncing around. There would be some potential energy, but it probably wouldn't be changing if we're just looking at some closed tank sitting at some point in space, right? So basically, how much energy do I need to add for a temperature change for a closed volume? That is the question that CV is asking. Now the more complicated one, or I guess they're not really super complicated, and that's CP. And this is our delta H, so internal specific enthalpy, divided by a change in temperature at constant pressure. So basically, this one's saying, hey, let's imagine I have a piston cylinder, okay? So I've got a container right here, and it's got a piston, bada bing, bada boom, straight lines because it does that sometimes. So we have pressure outside and we have pressure inside. And we know that those are going to equalize. So there's always going to be a constant, basically atmospheric pressure being applied to this closed system. Now, if we think about the energy balance, there's energy we can add in the form of heat and work and other things like that. I'm just going to collapse all of that into like E other. And then I'm also going to look at the work that's done across this boundary. So we'll just call this work boundary has to equal our change in internal energy. Again, you could look at KE and PE and things like that, but in this kind of idealized cylinder, it's not really moving around, and it doesn't really have, like, technically it would have potential energy if it's moving up and down, but we kind of assume that that's basically negligible. So my boundary work, if I'm looking at constant pressure, would basically be the integral, if you remember, of P dV. But if my P is constant, I can pull this out, and then I just get a delta V. So this becomes P delta V. And I'm going to put a negative sign out here because delta V is my final volume minus my initial volume. So if that happens to be positive, that means that my volume is increased, which means the piston is going like this, and there's work being done by the system. Now if I go ahead and I rearrange, I would get that the E other has to equal my delta U plus P basically times V2 minus V1. If you remember, U plus the product of PV is enthalpy. So this is the same thing as our delta H, which is where this is coming from. Basically the amount of energy I need to add, both in terms of changing the internal energy here and also moving, here I'll scroll up a little bit, this piston. So both of those energies combined are going to be the energy that I add to my system at constant pressure. How much of that do I need to add in order to change my temperature by 1 degree? That's what the constant specific heat at constant pressure means. Now if we go ahead and we combine this with the ideal gases, then there's some other stuff we can look at. So with ideal gas, okay, so remember that the definition of enthalpy, if we're looking at specific, is our pressure, sorry, not our pressure, our internal energy plus pressure times, since we're looking at specific, this would be specific volume. But if you remember our ideal gas equation, PV equals RT. If we go ahead, that's a terrible R. Come on, RT. Okay, this is the same thing as RT. So this is U plus RT. Now remember that we said U, as part of our theory, is basically a function of temperature for an ideal gas. So all the internal energy can basically be described by just the temperature. R is constant, and well, T is our temperature, which means that this entire thing right here is a function of temperature. So U is a function of temperature. I'm not really sure how I want to write this. Your notation can kind of be whatever. Just understand U is a function of temperature, and H is also a function of temperature for an ideal gas with these constant specific heats. And technically, in order to do this, getting our delta H, we would have to integrate. Like basically we would have to do, if you remember, so our CP is delta H over delta T. So we'd have to go ahead and say, all right, our integral of delta H would equal integral of CP delta T. Our CP is a function of temperature, so basically as you heat it up, the amount of energy you need to change the temperature by 1 degree would change. But our approximation, and this is where the constant specific heats part comes in, is we basically assume that it's close enough to constant over a process. Now if we look at this integration in the ideal gas case, we would go ahead and we would bring this down right here, and we would have that our dH has to equal our du plus r times our dt. And these may have to be inexact differentials. Remember, it's really just a notation thing. But if we bring in our specific heats, remember that our CV at constant volume is our change in internal energy over our change in temperature, and then our CP is our change in enthalpy over change in temperature. So if we plug these into here, what we would get is that our dH is CP dt, and then our du is CV dt, delta t. Man, I'm really just going crazy with what delta t's we're using. we'll just keep it constant with what we have here and do d, like a d for our differential, plus our dt. And now notice we can just divide out our dt's right here, and this right here is a pretty useful equation. So if you're looking at the specific heats, Cp for an ideal gas has to equal Cv plus R. So if you ever want to get between Cp and Cv, all you need to know is R. And then lastly, just another like kind of vocabulary notation thing, K is just like a number sometimes they'll give you, and it's equal to the ratio of our Cp to our Cv, just like this. It'll come up in later equations. It's basically just to keep us from writing Cp, Cv everywhere and all of that. But what if we're not using a gas? You know, we talked about the specific heats with the ideal gas, but what about liquids and solids? Because our specific heats are still a thing for liquids and solids. I know we talked about ideal gases right before this, but specific heats also apply to solids and liquids. Well, if you remember from earlier, we basically assume that solids and liquids are incompressible. So if I fill a tank right here, if you imagine, I fill a tank with water, and then I have, let's say I put a piston here and I try and compress this, you can't really do it. It's like really hard to compress water, or especially a solid. Like, can you just like take a piece of wood and compress it, make it go into a smaller piece, or any other solid like a block of metal or something? Probably not. And so our assumption here is that our specific heat at constant pressure is the same thing as our specific heat at constant volume, because you can't compress these things, and so we just call it C. And this right here is how you'd handle specific heats for solids and liquids.